here's where we left last time. So I want to try to build that. I want to try to build that basically on Quirk. So this is supposed to be a sample QAOA circuit with n equals 4, p equals 1. I kind of don't remember what p means really. Implement reverse Ising model. In the final project, we wish to know if we can find intrinsic patterns to the solution angles so that we can make more informed guess on the initialized input angles. Will look like this. The result processing contains two parts. Where the final state, the first term at the right, can be calculated directly based on the distribution of Z. I'm not so sure if I really understand all that. We use the Rigetti forest code, those circuits, and use Python to make pre-processing and post-processing. The post-processing of this for a 2-qubit system is given in Appendix A4. A4. Implementing MaxCAD. Two-qubit. Figures. P1 with P2. So that is supposed to be the result. After the composition. Question is whether this is something that's concrete for the MaxCAD problem, or is it something that is in general the QAOA circuit? So QAOA circuit. Let's see what we find. Quantum flow, QAOA, quantum. Now optimizing QAOA. Maybe in the Wikipedia there's something. Just want to contrast kind of. The quantum had a better approximation ratio than upon all time. Depends on 2p angles. Oh, so p is the amount of angles. Okay. These operators are iteratively applied on a state that is an equal weighted quantum superposition of all the possible states in the computational basis. In each iteration, the state is measured and the computational basis Caesar is calculated. After a sufficient number of repetitions, the value is almost optimal. Okay. Growth. What is growth? Quick start examples. Algorithm and details. So this is the MaxCAD problem. So this is how, okay. Maybe I'll go through that as well later. So here they're constructing actually the circuit. Okay, interesting. Gamma. Quantum processor, prepare quantum state, measure term 1, term 2, term n, Hadamarts, and then classical processor. So, yeah, but that's a bit of a different circuit, isn't it? Source code. Okay. Because those are pieces here that kind of repeat, and then there's these, and then there's like rotations on the x-axis. But I wanted to understand what is it that it's doing, and I'll probably just jump to Quirk right away, because here they explain the different pieces. Apply maxcat to QAOA. So that seems to be a specific circuit for maxcat. Maybe. Because the concept of QA, so the workflow, so this is all a generic thing. Okay, let's try to build that in Quirk, and then let's try to see if we understand what's going on. I also kind of probably should refresh a little bit because it's been a couple days. A lot of stuff going on. Good. So let's go back to what is it here? Control, target, whatever. So this is okay. Rotations, blah 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 blah. So let's try to build that. So first of all, we've got control knots. Then we've got in the middle a sort of a it's a Z rotation on a 2 times an angle. It's an RZ gate. So the RZ gate, which is parametrized, I would basically, because I can define that variable, I think, here. I'll have to make a custom gate, probably. And I would say it's a rotation, the Z-axis of like whatever angle. We'll just use 45, and I'll just call that like RZ, like 45. And then I guess if I do this, I can change the not much, because it's kind of that I could easily change here. I probably spinning 16 Z rotation. How can I make a Z rotation parameterized on some value A? Because those are parameterized, rotates target by input. It's a parameterized Z gate. Rotates the target by input A on the half turn around the Z axis. That's not what we want. We want a Z rotation that is kind of parameterized. Because I can definitely use an input A. I could definitely do something like that, and then I think that I could do something like that where I can just say whatever is the input I want. But then I would need that A would kind of need to do that, you know. Mm, and A would have to be, but this is just divided, and that's not what I want to do. I want to have like parameterized rotation, and making a gate is not, that's not definitely gonna help. Or can I put A here? No, go to 45. So then I'll kind of have to change that. You know, if we pick the different angle, then we'll have to kind of change that. I guess. So that will be a first attempt. Can I just, okay, that's not, okay, so I'll just use these for the moment, okay? Then it's kind of the same, right? So then you got this, and this, and this, and this, and here you got this, and then we've got this, we've got this, we've got this, we've got the same rotation, and now we've got the X and X here, with the control being here, and the same rotation, and then we've got a bunch of X rotations on some other angle. On some other angle. So, and here I'll have to make another gate on the x-axis, and this other angle I'll just whatever, like 50, 60 degrees, and we'll call it RX60. And it's like this, something, okay. It's already kind of an equal superposition, is it? No, no, it's not. Those are independent chances, okay. Those are independent chances. And now Hadamarts. Interesting shapes. Okay, so let me just bookmark that. I'll call this QAOA. Bookmark that, QAOA V1. So what this is kind of doing, if I'm putting this here, I mean, now it's nothing because it's like 0, 0, 0 here. But I'm kind of lost now. What was the purpose of the whole thing? Oh yeah, so we're supposed to kind of try an encoding, right? Exactly. So the idea is you try here you shoot it a possible. So how do we encode? That's the first thing. How do we? Because the idea is you shoot it here a possible max cat thing, I guess. Possible split, correct? No. Applying max cat to is interesting how different objective functions apply to. Take max as an example. The problem can be phrased this way. Suppose we have a connected graph. It can be determined by n vertices and an edge set. Size m, we can classify each vertex into one of the two categories by setting values +1, -1 belonging to a vertex. Okay, a cat occurs if two vertices of an edge disagree. So if this times this is -1, our goal is to find a classification such that we have the maximum number of cats or disagreements. So then it's sort of so then it's like it's about minimizing that, because a cat is a -1, so you want to minimize that. Okay, so this max cat problem can be translated in the quantum perspective in the following way. Consider n vertices as n qubits. Okay, n vertices as n qubits in computational basis, and regard the classification of a vertex as assigning the state of that qubit 0 or 1. Computational basis and regard the classification of a vertex. As assigning the state of that qubit 0 or 1. At the end of the day, measure the basis state z, which is a tensor product of 0 and 1, and giving the classification of qubits. In this way, all 2 to the power of n different vertex classifications correspond to 2 to the power of n computational basis. We still want to use a classical objective function, so we need to consider C as an operator. So Z, if the edge is a cat, 0 if the edge is not a cat. Still not so sure. As it can be seen, a phase is added to Z if 2 qubits are different. So if it is a cat, which is exactly what we want. Here it's explained like the maximum cat problem is the first equation describing the original quantum. It's probably similar to graph coloring. Given a graph nodes and edges color, said it a bit more formally. The problem is to partition the nodes of a graph into 2 sets such that the number of edges connecting nodes in the opposites is maximized. We have drawn the edge only in the line with the scissor indicates which set node. One can denote which set S or this node is with 0 or 1 respectively in a bit string of length n. Okay, so the zeros and the ones are the size zero. The four partitionings of the barbell graph listed above: 0, 0, 1, 1, 0, 1, 1, 0. For any graph, the bit string representation for any graph, the bit string representations of the node partitionings are always length n. The total number of partitionings grows as 2 to the power of n. For example, a square ring graph has 16 possible partitions. Yeah, of course. Okay, so 1, 0, 1, 0, 1, 1, 1, 0. Okay, so you're basically saying for each edge, we use 1 qubit. No, for each vertex, not edge. That's, I think, the same we're using here. The same concept. One, if edge jk is a cat, because I think it's a little bit different. Because the n vertices as n qubits. Yeah, vertices, exactly. Because the vertex sign is say 0, 1. Yeah, man, it's a bit late at night. Okay, boah. That's just simple. Okay. Okay, so what is it? What this is doing is we want it to be okay. So there's something here missing because there's like so you got to do some post processing afterwards. That's gonna be really confusing. So basically, what is x1? This is qubits. So and that's actually what this is doing is exactly. So what this piece here, basically what these pieces are doing are kind of rotating or adding negative phases for the qubits where we have rotating the phase for the qubits where we have a 1. Yeah, is that correct? Seems so. There's a result. Gates and yeah, but those are controlled rotations, really. Okay, I think that's kind of what it's doing. Can implement using C0 gates and RZ gates. The second part is a phase change which can be done using So a phase is added to Z if 2 qubits are different. Cat, which is exactly what we want. Really? The normal flow is the same as cat. However, some simulation can be performed based on the property of the graphs. First, for each edge, we only need to evaluate a subgraph that is p steps away. Blah blah blah. That's the simplifying. The second layer of simplification is that only some of the edges need to be evaluated. It is based on observations that subgraphs. In the final project, in this final project, found interesting pattern to solution angles. Visualize input angles. But I still don't get what is then. So is it QAOA just a general concept for? Because if so, I'm just gonna stop here, people. Is it just QAOA the concept of make a cost function circuit parameterize it, change the angles, and just figured it out? Like, is it really like that? Quantum approximation optimization algorithm is one of the algorithms that can be implemented in the aircraft. QAOA is a approximation algorithm, which means it does not deliver the best result, but only. And this will introduce how it works. Okay. So because I was just like thinking, so here, classical solutions, details, some terms, classical optimization of Ansatz parameter. Try again. So if I say, let me just clear that. If I say, I don't know, 1 and 1. Okay, so I'm taking the Hadamard's first of all. So that is indeed changing some of the probabilities. Chance display. So if I add the Haramarts again, what was the difference? Now I get like an equal superposition, right? Yeah. 1 0 1 0. Yeah, but that's the one. That's the input. Those confuse me a bit first because there's like, yeah, but those are the individual qubits. Yeah, I mean, again, like just I pick random angles and that's just, stupid because if I need to be able to, I need to figure out a way to parameterize because I'd like to just put input A, like sort of put a default somewhere and then use A input. You know what I mean? Just use the A input somewhere and then the B input, the B default, and then use those to parameterize this. But the only way that I can parameterize that is the Z's are like that. And what I'm interested in doing is parameterizing something like this, okay? But isn't it possible for me to parameterize based on because now I'm going to change basically all these gates by myself. There's no way that I can edit that, correct? Unless so here I see the last one kind of. Okay. Problem statement, blah blah blah. So, but it seems like if some a bit kind of deceived in the sense that I think it doesn't make any sense. It's not something I want to explore farther. If this is really the gist of this, it's basically coming up with whatever circuit that is the cost function in your problem, and then just parameterizing it. And then, I mean, it's not to diminish the meaningfulness of this, it's just that it's not what I want to explore right now, because it's kind of easy from the perspective of intuitively understanding that is easy. You don't need to build that. But it's definitely, I mean, how can I just, this I like to know. Um, yeah, but it seems like, because this is a really generic, there's sort of a generic explanation, discussion about use, like a generic, some of the explanation might be trivial to readers, blah, 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 problem statement. For side details, strings, I see the substance of the system priority. So, suppose we wish to maximize, here's sort of a generic explanation, maximize an objective function. Strings that see if substring satisfies certain property. For example, C1, okay. Even approximation solution is all we need. There are many. However, we probably can do better using quantum approximation. The first step is to treat the objective function as an operator. The C has eigenvectors Z. Yeah. Maybe there's just some constraints in the way you define the circuit. If we measure it in Z, each result is a single basis state. And then there's a state interesting. T means trial decomposition, and there's an angle which will come back later. If to our commute. There seems to be a bit more to it, really, but I certain component Z. This means for certain component Z, a phase will be added in front of Z for each of the satisfied conditions. This can be easily translated to an explicit circuit using controlled phase gates with the help of an ancilla qubit. An ancilla qubit is not always required. Yeah, but so this is what we're doing. So it's controlled gates. Okay, so it seems like control M with CM. I mean, no, really. It seems that has that specific structure, but then I don't understand why in the Yellow Submarine project we're using like other stuff. We're using like the continuous, like the CV quantum computing gates, squeeze gate, and all this kind of stuff. Maybe there's just a version. If I Google like CV QAOA, do I get any results? Because if this is really like that, I'm just moving forward, people. For example, the rational quantum eigensolver has been used for searching the ground state, and VQE seems to be the same. Similar, the quantum optimization has been used to find approximate solutions of classical Ising models. Okay, and clustering problems formulated as maxcut. Okay. So those seem to be specific circuits that you can parameterize, and they help you find approximate certain solutions. It's nothing else than just a model. You remember there's another video that I did where you've got like you had a different another kind of model. So this is just a model, and that's definitely. I mean, this is interesting, but I don't think that I'm going to dive into this further. Intuitively, so intuitively, I mean, I'll you know what? I'll just let's do the following. I'll do another video on this. Try to understand intuitively that particular model. With the rotations here and but basically that's then you just parameterize and that's it. There's no more magic to it. It's just a um, it's just another way to do machine learning, really. uh, yeah, probably do that. Kind of trying to understand what's the advantage, the quantum advantage here. It's maybe the fact that you've got like the fact that then you put that into superposition. Like I think the trick here is one of those Hadamard is doing, right? And then because you've got like the what are those graphs? And you got whatever the result is. Yeah, traversize with P1. That definitely is telling you the solutions. Kind of. Okay. But you gotta fine tune then the angles. I think I'm kind of almost there. I just wanted to. So I basically built it this way, but I don't know how to parameterize that in an easy, in a more comfortable way. So I can just change the number easily, so without having to build the gates again and replace them. But once this is done, then I just need to understand sort of intuitively what is it doing. But it seems simple in the sense that it's doing a control phase rotation. Yeah, but then if I do the amplitudes here now and the amplitudes here fixed, or the amplitudes here, but the phase hasn't changed. Oh, here the phase has changed. It's the same. Here the phase has changed. The relative phase. Yeah, whatever. I have to figure out how to work with that a bit better. But let's see. Let's see if I understand that. Cool. Yeah, I think that's going to be the next step. But it's basically intuitively that. So it's just parameterizing a model and then getting a set of solutions and seeing if you're kind of happy. And then, okay, basically that's what it's doing here. And then doing the optimization of the ansatz parameter. The ansatz parameter being probably the angles. Yeah. And I'm assuming VQE for chemistry will be the same. So I won't spend much time on that. I'll move forward to other stuff that are a bit more sort of quantum-ish, or a bit more, I don't know, of my liking, I guess. Cool.